Hello student. From chapter 7 wave optics we have to start new article and it is diffraction of light. Now first thing, what is diffraction of light? Basically diffraction of light is the bending of light. Now you know that you already learn a concept, refraction. Refraction means what? A bending of light when light travel from one medium to another medium. That bending is the refraction. But here in a diffraction, light bend, but it bend round the edge of obstacle, and that bending of light is called as diffraction. Means if this is object, this is screen, light is coming here and it bend from this edge of the obstacle and incident here. So that kind of bending is called as diffraction of light. So I hope everyone understood diffraction. In diffraction, a source is coming, source of light. This is obstacle and this is screen, on which we can see the diffraction pattern. So this diffraction means bending of light round the edge of obstacle is called as diffraction. I hope everyone understood what is a diffraction. Now, diffraction is classified into two types. Now we have to learn the types of diffraction. Types of diffraction. First type is Fresnel diffraction. Fresnel diffraction. And second one is Fraunhofer diffraction. Fraunhoffers diffraction. Now let me learn what is Fresnel and what is Fraunhofer diffraction. Now just I told you, in diffraction, three things we have to consider. The first one is source, second one is obstacle, and third one is screen. So these three are very important here in diffraction. Now Fresnel diffraction is a diffraction pattern in which distance between source and screen, it is a finite. Distance is finite. As well as distance between obstacle and screen is also finite. So we can say that Fresnel diffraction means the diffraction pattern in which source and screen, see the diffraction pattern in which source and screen are placed at finite distance from obstacle is called as Fresnel diffraction pattern. So here source and screen are at finite distance from obstacle. Take it. Now here distance is finite, and because of that generally here this Fresnel diffraction is produced by a point source or spherical wavefront, produced by spherical wavefront or cylindrical wavefront. So these two wavefront can produce Fresnel diffraction pattern. Now Fraunhofer, what is Fraunhofer? So here distance is finite and here it is infinite. Means here obstacle screen infinite distance, source obstacle again infinite distance. So in simple word we can say that the diffraction pattern in which screen and obstacle and source are placed at infinite distance from obstacle, that diffraction pattern is called as Fraunhofer. So I can use the same wording here, infinite distance from obstacle. Now here next thing is, here we written it is produced by spherical or cylindrical wavefront. So this Fraunhofer diffraction is produced by plane wavefront. Why plane? Because you know that if the source of light is at infinite distance from obstacle, then that wavefront is a plane wavefront, because plane wavefront we get at infinitely large distance and it is produced by point source. Plane wavefront means what? the wavefront we get at infinitely large distance is the plane wavefront. So here, produced by plane wavefront. I hope everyone understood the diffraction and types of diffraction. Now after that we have to learn Fraunhofer diffraction due to single slit. So next article is Fraunhofer diffraction due to single slit. ठीक है. Fraunhofer's diffraction due to single slit. Fraunhofer means the diffraction pattern in which source and screen are at infinite distance from obstacle. Now I consider. Here this is slit. Slit means a gap through which light is coming. This is slit. Take and this is a plane wavefront. So this light is coming. So source of light is at infinitely large distance. This source of light is at infinitely large distance. And so here from the edge of this slit, light get diffracted and we get diffraction pattern at infinitely large distance. Now, if we get a diffraction pattern at infinitely large distance, how we observe it? So we have to bring it closer. So we have to bring that diffraction pattern closer. So we can do one thing here, we can keep here a convex lens. So because of that convex lens, we get a diffraction pattern in a focal plane of the lens. So I can consider here a convex lens. So this is a convex lens. And due to this lens, we get a diffraction pattern in a focal plane of this lens. So I consider this is screen. So this is central point. So we get here central bright point. And here some light may be diffracted like this. And because of this light, we get here point P. Now this point P may be a bright point, dark point, we don't know. So we don't know here the point P is what. Now here, I can consider this is a slit AB and here this width of this slit AB is A. This is slit width A. Now I can draw a dotted line here. Now I have to explain this diffraction pattern and we have to obtain the conditions here. So conditions for maxima point and minima point. For maxima, I can write here or I can do one thing here. Path difference I can write. One light wave from this point reach to point P and another light wave from this point to reach point P. Then how much is the path difference? If I take the subtraction, we get a path difference. Listen, to get path difference, if I draw a perpendicular line from this, so this is 90-degree line. So this is B and let I name this point as a E point. So I will give the name here. So here, this is B and this is E. So A to P and B to P, if we subtract this distance, we get B is the path difference. So here, path difference is BE. This BE. Now see here, if I use this triangle and if I consider this angle is theta, then BE is what? Opposite side. Then we can use sin theta. Sin theta is opposite side BE upon hypotenuse is A. So by using that, BE is what? A sin theta. So we get path difference is A sin theta. So I can write here is equal to A sin theta. This is the path difference. Now I can write a condition for maxima and condition for minima. For maxima point, A sin theta is equal to, and here I am writing for minima point. For minima, path difference A sin theta is equal to. Now we have to obtain these conditions. Now to obtain condition, initially I consider this is slit again. Okay, let I show it larger. Okay, this is slit. These are the light rays. I mean, this is A, this is B. Okay, and light rays are going like this. If I draw perpendicular line here, we get BE point. Okay, same diagram I drawn it here for the explanation purpose. Now, one light wave start from this point and reach to the point P. Another light wave start from this and reach to the point P. And another light wave from this start here and reach to the point P. Now, light wave reaching from A to the point P and this light wave reaching to the point P having a path difference. Now, you can see here. So this is the path difference, and that much distance is stand for one crest only, and distance of one crest is lambda by 2. So here between these two, path difference is lambda by 2. Okay, path difference is lambda by 2. And if path difference is lambda by 2, so we already learned the condition for the interference here. If path difference is odd integral multiple of lambda by 2, 1 into lambda by 2, then we get destructive interference. So here, a light from A and light from this point reach to the point P, and the path difference is lambda by 2, so we get a destructive interference. This light wave cancel with this, and we get a dark point at this point. Similar manner, dark or minima point we can say. Similar manner when we are talking about these two, so wave from this and wave from this. So how much is the path difference between these two? So that much. Sorry, not that much. So again, this is the difference. So here one crest is already there, here one crest, and we can say that a distance is this much, one trough distance. So again, the path difference between these two is lambda by 2. So light wave from this point and this point reach to the point P, and the path difference is lambda by 2. Again, we get a destructive interference and they cancel with each other. So here we get no light at point P, or here we can say that minima point, we get minima point. So here listen, in diffraction pattern we are not getting perfectly dark point and perfectly bright point. So we get here maxima. For the bright point we can call it as the maximum intensity point, and dark point we can call it as minima point. Now here we get minima point. Now when we are talking about point A and point B, how much is the path difference? So here wave start at origin means 0, and here it is this much and this much. So total distance is lambda. So total distance is lambda. So point A and point B, so this much BE is the path difference, and path difference in term of lambda is lambda. So here, and we get minima point. So for minima, first minima we get when the path difference is lambda. Now next time, I have to consider this slit is divided into 3 equal parts. Now I consider the same slit and I divide this slit into 3 equal parts. So 1, 2. Okay. You can draw this line. Now see here. So here we get like this, and here again here when we divide the slit into 3 equal parts, then again the light wave from this point and this point having a path difference lambda by 2, this point and this point having lambda by 2. So these two light cancel with each other at point P, these two light cancel with at point P. Okay? And here again, listen, this lambda by 2 means here light wave from this and this, they cancel with each other. So light wave due to this lambda by 2 and lambda by 2 get cancelled. And this lambda by 2, light wave due to this lambda by 2, we get at point P. Listen. So light wave due to this lambda by 2 get cancelled with each other, and this lambda by 2, due to this lambda by 2, we get a light at point P. So here we get maxima point. So here we get maxima point. So here we can say that a path difference between A and B is So here lambda by 2, lambda by 2 and lambda by 2. 3 times lambda by 2. That time we get a maximum point. So here maxima 3 lambda by 2. First maxima point we get at 3 lambda by 2. Now next time when we divide the slit into 4 equal parts. So here 1, 2, 3 and 4. So ठीक है. So this lambda by 2, this lambda by 2 light get cancel. Again this lambda by 2 and this lambda by 2 light get cancel. This light get cancel. We get again here minima point. So here part difference between A and B. Lambda by 2, lambda by 2, lambda by 2, lambda by 2. 4 times lambda by 2 means 2 lambda. Next time 3 lambda. We get minima point. 4 lambda and so on. Similar manner, now here I consider slit is divided into 4 equal part. When I divide into 5 equal part, the light due to the 4 parts get cancelled. And due to the 5th part, we get a constructive interference at point P and we get a minima point. Now, so we get, maxima point. So here the part difference is coming 5 lambda by 2. Next time 7 lambda by 2, 9 lambda by 2 and so on. So listen here. So here we get a light at point P because of 1/3 part of the slit, 1/5 part of the slit, 1/7 part of the slit, and because of that whatever the light we get because of this and because of this. So because of this 5 lambda by 2 lesser light at this point P, lesser light at point P due to this part difference. So here intensity of light goes on decreasing in this diffraction pattern. So here in general we can write formula. See here, I can write part difference A sin theta is equal to, I think this is visible, na? So not visible, I will write it here. So I write this part again below. For minima, A sin theta is equal to, I write the same thing, lambda, 2 lambda, 3 lambda, 4 lambda and so on. And here for maxima point, part difference A sin theta is equal to how much we get? 3 lambda by 2, 5 lambda by 2, 7 lambda by 2, 9 lambda by 2. Okay. Now up to that, we can write this in term of formula A sin theta is equal to 2n plus 1 lambda by 2 for maxima. This is condition for maxima. And this is for minima. A sin theta is equal to n lambda. Now here in interference we get n lambda. Part difference is n lambda for bright point. But here we get for minima point, means for dark point we are getting this n lambda. And in interference, part difference is 2n minus 1 lambda by 2 we get for dark point. But here we get plus, and for dark we get in the interference, here we get for bright. So why this plus sign? Because, so first maxima we get at 3 lambda by 2. We are not getting maxima at lambda by 2. We are getting first at 3 lambda by 2. So the plus is coming here. If I substitute n is 1, 2 plus 2 into 1, 2, 2 plus 1, 3, 3 lambda by 2. So we are not getting first maxima at lambda by 2, we are getting at 3 lambda by 2. So because of that plus sign is coming here. These are the condition. And if you see the diffraction pattern here. So this is intensity axis. And if I consider here sin theta, then we get this type of graph. So this is principal maxima, then first minima and so on, like this. So this is called as principal maxima. or it is also called as central maxima. So this is central maxima. I can show it here also. So here we get principal maxima, and there here maybe a minima, or I can take a first maxima also, and so on, like this. Then this is first minima. So this is first maxima. This is second minima. This is second maxima, and so on. Similar manner here also. First minima, first maxima, second minima, second maxima, and so on. And if I written a formulas of sine theta here, so here we get minus lambda by a, minus 2 lambda by a, and so on. So here plus lambda by a, plus 2 lambda by a, and so on to this side also. So this is the intensity versus sine theta graph. I hope everyone understood this. Now I can write here the formula of slit width also, formula for distance, width of central maxima. Width of central maxima is this distance is lambda by a, this is lambda by a. 2 lambda by a is the distance of central maxima in term of angle, in term of sine theta. So angular width of central maxima is equal to 2 lambda by a. So in term of distance, width of central maxima is equal to 2 into this bandwidth. So 2 into lambda into this d by capital D. So here we know the width, fringe width formula, lambda d by d. Okay? So this width formula everyone know, lambda capital D by d, capital D by d. Okay? So here A. So this is the formula when we are talking about width, and where angular width it is coming this. So that you remember. So angular width. How we get this formula? Or you can write angle also. So by using this formula, you can write angle also. So you know that a sine theta is equal to n lambda. Okay? Then sine theta is equal to, for central maxima, n is 1. For maxima, n is 1. So I can write a sine theta is equal to lambda. So sine theta is equal to lambda by a. So theta is equal to sine inverse of lambda by a. So this is theta. And angular width of the central maxima is 2 into theta. I can write. So 2 lambda by a, 2 theta. So here I can write 2 lambda by a. 2 theta I can write, and theta is what? Sine inverse of lambda by a. Then 2 sine inverse lambda by a. But this theta is very small, so sine inverse, instead of sine inverse, I can write only lambda by a. This angle is very small, so I can write theta nearly equal to lambda by a. So exact value is sine inverse of lambda by a for theta, but I am using lambda by a. So here lambda by a. If I write the exact one to into this, sine inverse lambda by a. This is a formula for angular width. Okay.